Okay, we're in the second video for Chapter 8. We've been discussing SN2 reactions, and one of the things we haven't talked about that we said we would was nucleophile strength. For an SN2 reaction, we said we wanted a good nucleophile, and we said we discussed what that means. So a good nucleophile, or nucleophilicity, the term itself, is defined as the relative rate of reaction for competing nucleophiles. So the word nucleophilicity is a kinetic term. The more nucleophilic you are, it means the faster you react in a reaction versus other nucleophiles. So let's compare, as an example here, we have two different nucleophiles, nucleophile A and nucleophile B, reacting. And they're both reacting with the same alkyl halides, with the same solvents at the same temperature. So everything's the same for these nucleophiles, the nucleophile conditions, except what nucleophile is reacting. If we form the substitution product for nucleophile A and nucleophile B, and we track the rates at the reaction of each reaction, the one that does the substitution the quickest will be the better nucleophile. So if the rate of reaction A for nucleophile A is greater than the rate constant B, or the rate of reaction B for nucleophile B, then that means that nucleophile A is the better nucleophile because it reacted faster. So, nucleophile strength, what makes you a good nucleophile or a strong nucleophile? Well, it generally increases with base strength. So if you don't remember what makes a good base, okay, then you need to go back to Chapter 1 in the acid-base chapter and reread over that, because that's going to be important that you understand what makes a good base. But if you're generally a strong base, then you're a good nucleophile. So here's an example. If we compare both of these compounds here, hydroxide and water, and I say both of these are bases because they both have electrons that are available for attack on the oxygens. The difference between hydroxide and water is that hydroxide's oxygen has 3 lone pairs, so it's got a negative charge, and the oxygen over here, even though it has lone pairs, is neutral. Which would you say was a stronger base? I think we all know the answer to the question, that hydroxide is the stronger base. So, if you're comparing atoms that are the same, but one of them has a stronger charge, is more negative than the other, it's a stronger base. It turns out it's also a better nucleophile. So a better base is a better nucleophile. Alright, so we're comparing two atoms, they both have lone pairs. Hydroxide's negative, water's neutral. The more negative the nucleophile, the better the nucleophile, the stronger the base. So, when we compare these similar atoms, if we reacted hydroxide with, say, methyl iodide, that's our alkyl halide, versus water reacting with methyl iodide, our alkyl halide, and we looked at the rate of these two reactions, because this is the stronger base, we see that this nucleophile would react fastest under the similar conditions. So because this is the faster reaction, this is the better nucleophile. It reacts faster. Alright, so the stronger the base, the better the nucleophile. Alright, the next thing we know about nucleophiles is that what if you're not comparing similar atoms, like an oxygen versus an oxygen, a nitrogen like an amine versus an anion nitrogen that's negative like an amide. So, what if you're comparing different atoms that have lone pairs? Well, if you're comparing different atoms with lone pairs, the nucleophile strength decreases with increasing electronegativity on the atom. The nucleophilic strength, its ability to react quickly, decreases, or is less, when you have a stronger electronegative atom that the lone pair is on. Now let's think about what electronegativity means. Electronegativity means the atom pulling the electrons in toward its nucleus when it forms a bond, or is going to form a bond. So let's take an example of hydroxide versus fluoride. Here we have oxygen with a negative charge, and we've got a fluorine with a negative charge. That's where our lone pairs that are reacting are. Okay, so that's our nucleophilic atom. When we look at them, we say fluorine and oxygen have the negative charge, but they both have negative charge. However, they're not the same atom. Which is the better nucleophile? The less electronegative atom is the better nucleophile, which is oxygen. And here's why, down at the bottom. Remember that if you're more electronegative, your valence electrons are held more tightly into the nucleus. So for fluorine, which is very electronegative, its valence electrons are held in very tightly, so they're less reactive. The oxygen is less electronegative, so its electron density is held much further from the nucleus. So when it reacts with the backside of an alkyl halide, it's able to form that bond quicker. Alright? So that's the next trend. So if we look here now, hydroxide versus fluorine, we've got a negative charge on oxygen versus fluorine. Now we need to compare negative with negative and neutral with neutral when we do this. So here I have two negatives. So the hydroxide is less electronegative. The oxygen is, so that's the better nucleophile. Here we have sulfur versus phosphorus. Phosphorus is less electronegative. It's got a pair of electrons there. These are both neutral. Than sulfur. So because phosphorus holds it more loosely, it's a better nucleophile. Those electrons are available for attack. And then we also have, over here, an amine versus water. So we have ammonia versus water. Now they're both neutral, okay? So it's not a negative versus a neutral. Usually the negative always wins. Nucleophiles are negative, are better. But since they're both neutral, we look at the atoms that have lone pairs. The oxygen versus the nitrogen. Nitrogen is less electronegative than oxygen, right? So it holds the electrons more loosely, so it's more able to form a bond with the alkyl halide. So that will be the stronger, or the better nucleophile again. So first we can compare the base strength. Negative is better than neutral. If we're comparing different atoms of the same charge, then we're going to look at, next, we're also going to look at the electronegativity trend. So the last trend only works when you're going left to right on a periodic table. Oops. So if you're going left to right on a periodic table, you see that the oxygen and fluorine are in the same row. So we can compare things that are on the same row with each other, the same period, because their valence electrons are found in the same shell, the equal distance roughly from the nucleus. It's just how tightly they're held. What if we're comparing atoms that aren't the same, and they're not even on the same row, they're in the same column? We're going to look, if we're going down the periodic table, not across, we're going to look at nucleophilic strength increasing as you go down, because those atoms become more polarizable. So as you go down the periodic table and compare atoms within the same column, you're going to try to find ones that are larger atoms. Their electrons are held less tightly, and they're more polarizable, or able to reach and form a bond. So polarizability is the nucleophile. The polarizability of the nucleophile is the atom's valence electrons are able to flow more freely and move to form bonds in a transition state. I think I said that really horribly, but let's say it again. Polarizability of a nucleophile involves the atom's ability for its valence electrons to flow easily and to create bonds more quickly to get toward a stabilized transition state. So a visual example is good for this. If we're looking down the halogen series, we've got fluorine, chlorine, bromine, iodide. And let's say that we're comparing nucleophiles, or negative ions of these. Alright, so they're negative. If we want to know which is the best, we want to find the largest atom because its electrons are the furthest away from the nucleus and they're more polarizable. Remember, fluoride's the smallest, and we increase size and polarizability as we go down the periodic table. So our strongest nucleophile would be iodide because it's the most polarizable. Its electrons are held loosely, further away, and those electrons are able to polarize or move and reach forward into the antibonding orbital, the back orbital of the alkyl halide, to form a bond quicker than the fluoride is able to put its electrons in this orbital. So if you're more polarizable, kind of like I say, fluffy and soft, then your electrons can move and mold to form that bond much quicker. So larger atoms, further down the table, those ions are better nucleophiles. Alright, so let's look at some examples comparing some different sets of nucleophiles. We've already talked about the halide series. We said as you go down the periodic table, the atoms get larger and they're more polarizable. So the more polarizable, the better they are at nucleophilic character, at being able to increase the rate of the SN2 reaction. So iodide's the largest, so it's the best nucleophile in the halogen series, then bromine, then chlorine, then fluoride. Alright, let's look at some others. What if we were comparing the sulfide versus the oxide anion? Which is better? Which is a better nucleophile? Well, on your periodic table, sulfur is lower on the periodic table than oxygen in the same column, alright, or in the same group. So sulfur is a larger atom than oxygen, which means its electrons in its valence shell are held less tightly, which means it's more polarizable and can form a bond more quickly as the electrons flow. And if you can be more quick, you're a better nucleophile. So the larger atom containing the nucleophilic charge is the best nucleophile. So far, our better nucleophiles are the larger atoms. Notice we're comparing similar charges again. Negative is always better than neutral for nucleophiles, but if you're comparing similar charges, then you've got to compare other things, like electronegativity and then atom size, depending on if you're in the same row or the same column. So let's look at this final example. Here we have nitrogen and amine, a triethylamine versus a triethylphosphine, the phosphorus compound. Now, on the periodic table, phosphorus is below nitrogen in the same group, so phosphorus is more polarizable. Electrons are held less tightly, further away from the nucleus, more able to complete that bond faster as the electrons are able to flow more. They're held in less tightly. So phosphorus is the better nucleophile versus nitrogen. Alright, now there's something else we didn't talk about. Notice whenever I compared phosphorus and nitrogen, sulfur and oxygen, the R groups were always the same, the backside of that nucleophile. Well, we need to talk about the steric or bulk effects on the backside of the nucleophilic atom. So what's bonded to the nucleophilic atom can increase or decrease the rate of the SN2 reaction, or the substitution reaction. So bulky groups decrease the strength of the nucleophile, which means they slow down the reaction. The bulkier the group, the slower the substitution. The bulkier the group bonded to your nucleophile, the slower the substitution. Now let's think about why this is. We know that nucleophiles, when they attack for a substitution, like an SN2 reaction, they do a backside attack. We've already talked about how the R group needs to be open in the back, the alkyl halide R group, so that it needs to be open back here so that the nucleophile can fit in, so that it can come and make a bond in the antibonding or the backside to kick out the halogen. But the other thing we need to think about is the bulk of the nucleophile. If we have a really small nucleophile, it's very easily, even if you have, let's say, a secondary alkyl halide, if you have a secondary alkyl halide, it's somewhat bulky back there. But if you have a very small, less bulky nucleophile, it can get in and it can still form the bond. There's room in the back. However, if your nucleophile is bulky, let me redraw this. Maybe it's really large this way. The alkyl group, whatever's back here, is very large. then you're going to have a lot of steric collision trying to get into the backside, and you won't get a good bond forming quickly. So bulky is worse, small is better. Kind of think of nucleophiles as a bullet. You want something very streamlined coming in. The smaller or less bulky your nucleophile, the better the nucleophile. So if you're comparing nucleophilic atoms and everything's the same, like for instance here, we both have oxygens here. They're both negatively charged. So they have the same electronegativity, the same size, the same charge. The only thing that's different is what's connected to these oxygen anion nucleophiles. Back here, our R group is a methyl group, which is relatively small and non-bulky. But over here, we have a T-butyl group. A T-butyl group is very large, and it takes up a lot of space, and it can be very bulky. So it makes it very hard to get into the backside of an alkyl halide. Too much bulk, the reaction won't occur, or it will occur much slower, we should say. So, which is the better nucleophile? The smaller nucleophile is better when everything else you're comparing is the same. For instance, here we have an amide versus a diisopropyl. We have two isopropyl groups, amide anion. They're both nitrogens with negative charge, so the nitrogen itself is a good nucleophile. It's negative. However, this is the less bulky nucleophile, so it can get in and react quicker from the backside. So when we put all this together, the negative charge versus neutral. Negative is better. It's a stronger base than a neutral. If you're in the same row, the less electronegative atom held electrons less tightly, so they're able to form a bond. If you're in the same column, the larger atom holds their valence electrons less tightly, so they're more polarizable and form bonds faster. What if we have a million things to compare? How do I know what are my good nucleophiles and my not so good nucleophiles? Well, here's a good list to start looking at. And while I wouldn't say memorize it, I think it's actually a good idea to dissect the list to the point where you pretty much know the list inside out. It's not that hard if you start looking at what we've got here. So we've got three different sections. We've got good nucleophiles, moderate nucleophiles, and poor nucleophiles. Now remember what that means. Good means you react the fastest. Moderate, somewhat slower, and poor, very slow. Not good nucleophiles. So if we look up in the good category first, all right, let's concentrate on that. Let's look at the first line. The best nucleophiles here are the least electronegative, and they are the largest. Iodide and bromide. Iodide and bromide are very fast reacting nucleophiles. Then, also just below that, but also fast, are your sulfides. They're not very electronegative, and they're larger atoms as well. Notice they're anions. Notice everything in the good category is an anion. All right, now, our next row are oxygens. See, we have oxygen anions. Hydroxide, alkoxide, okay, OR minus. So after the sulfides come the oxides. So we've got the big halides, the sulfides, the oxides, and look here. That's our acetylide from chapter 6 when we deprotonated the terminal alkyne. Now just below it we've got cyanide. Remember, cyanide's a negative charge on carbon. This is just the condensed structure, CN negative, but it's the negative on carbon. We've got the azide, nitrogen, 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 negative charge overall, okay? And then we've got the amide. So the nitrogens are last. So it's always a great idea to know your good nucleophiles. The large anion halides, bromide, iodide, the sulfide anions, the alkoxide or hydroxide ions, acetylide, and then we've got our cyanide, our azide, and our amide. Okay, let's look at moderate. Our moderate nucleophiles, half of them are negative and half of them are neutral. So all of our goods are negative. There's a few negative nucleophiles that are not good. They're moderate. They are our smaller halides, chloride and fluoride. And then look at these oxides. They're not like the oxides up here. They're anions of oxygen, but notice they're next door to carbonyls. These are carboxylate anions. Now, what makes a carboxylate anion less reactive? What makes you less reactive is that you're more stable due to resonance. Remember we talked about that in Chapter 7? So because these anions are resonance stabilized, they're less reactive oxygen anions than the oxides above. But they're negative, so they're moderate. Now we come down to our neutrals. Now we have our neutral sulfurs, the thiols and the thioethers. And then we have our neutral nitrogens, our ammonia and our substituted amines. So over here we had the nitrogen anion. Here we have the nitrogen in the moderate group when it's neutral. We had the sulfur ions, and now we have the neutral sulfur series. So we see as we go from negative to neutral, some of the best are becoming moderate. Now what about the oxygens? Remember the oxygens were below the halides and sulfides. So it turns out that when you have neutral oxygen nucleophiles like water, alcohols, and acids, they are the worst nucleophiles. Remember they're also bad bases too. So your good neutral weak bases are in moderate, but your weak, really weak bases, which water, it's neutral, your alcohols, and your carboxylic acids, they're not good bases, right? So they are the poorest. So putting it all together, this is what nucleophilic strength kind of looks like. Here we have our best nucleophiles and our slowest nucleophiles. So now that we've covered nucleophilicity on how fast or successful an S&2 reaction is, or substitution reaction, we're going to talk about leaving group ability. Not only does a nucleophile have to form a bond quickly in order for an S&2 reaction to be better, but the leaving group has to leave quickly and not return, or else you'll reverse the reaction. So our leaving group here, remember in this chapter, will be the halides. So halides can either be fluoride, the leaving group when the nucleophile comes in can be chloride, it can be bromide, or it can be iodide, because all of these are halogens attached to the alkyl halide that will eventually leave. So when we look at this reaction, in order for the reaction to be successful or to go right, to form products, we want to form an anion that is stable. In Chapter 1, we talked about what stable anions look like. We talked about acid-base chemistry. So the leaving groups are anions. We want them to be stable. We need stable anions. So go back to Chapter 1 if you don't remember what a good conjugate base, stable anion base looks like. Remember, it starts with atom size and everything else. So go back and look at that, but we want a stable anion. And when we say stable anion, basically what we mean is we want a weak base. We want a weak base. Weak bases are stable. Strong bases, like hydroxide, I know that's not a halide, but that would be a horrible leaving group. It's very reactive. So looking on, what makes a good leaving group? We said it had to be a stable anion. And the reason this is true is because you want a lower activation energy for a fast reaction. A good leaving group is able to stabilize negative charge on the developing transition state. You want a stable anion. Stable anions are weak bases. Okay, they're not strong bases. So if we look at the acids here, the strongest acid we have is HI. HI is the strongest acid. It has the lowest pKa. Alright, so if you're the strongest acid, your conjugate base is the weakest. So it turns out the best leaving group, the most stable anion, is iodide because it is the strongest acid of the series. So iodide is the weakest base. So it's the best leaving group. It's the best leaving group. The worst leaving group is of our weakest acid, it would be our strongest conjugate base. So the series runs that iodide is the best leaving group, then bromide, then chloride, and then fluoride is the slowest or worst leaving group.